Okay, here is the first step in deriving the shape functions of your triangular element. Now, if you have not watched the part 1 of this video, I highly recommend that you please go back and watch the part 1 of this video so that there is a continuity. Okay, there is a triangle and I'm going to reckon a set of coordinate axes. This is the x-axis, this is the y-axis, and I'm going to mark the nodal points. This is nodal point number 1, this is nodal point number 2, this is nodal point number 3, and I'm going to mark the displacements of the nodal points. Well, the nodal point 1 can get displaced along the xy plane in any direction. It depends on the type of load. It depends on the nearby triangles. But that really doesn't matter. What really matters is it can get displaced along the xy plane. That is what matters. What also matters is you have to understand that it cannot get displaced along the z direction. Okay? So this is the x-axis and this is the y-axis. This nodal point 1 can get displaced along the xy plane. It cannot get displaced, along the z direction. This is one thing. The other thing that is to be noted is the point that is beside this nodal point 1 along the z direction. So this is along the z direction. This is an exercise for your imagination. Okay, I hope everyone is able to imagine that it is along the depth direction. Maybe you can call that as 1 dash to separate that from nodal point 1. It is 1 dash. This red fellow, how do you think this red fellow is going to get displaced? The red fellow gets displaced in exactly the same fashion as nodal point number 1. So I'm going to say the statement one more time. This red fellow also gets displaced in exactly the same fashion as nodal point number 1, which means that the white arrow and the red arrow, they are parallel to one another along the depth. But of course, this is a two-dimensional representation of a three-dimensional situation, so it is difficult for me to represent here. It's a very poor representation, but I hope everyone can understand this point that the white fellow and the red fellow, they are getting displaced by exactly the same amount. This is important. Why do you think this is important? Only then you can say that this is a two-dimensional element. Okay, suppose the red fellow is getting displaced by a different amount, by a different magnitude compared to the white fellow, then it is not a two-dimensional element. It becomes a three-dimensional element. Hope that is clear. So clearly the displacement is a function of x-axis and y-axis. Definitely it is not a function of z-axis, because all the fellows that are parallel to the white fellow, the white, the red, the yellow, the blue, all these fellows are getting displaced in exactly the same fashion. So you don't actually need the z-axis. You don't have to analyze any plane along the z-axis, because all the planes that are sliced across the z-axis, they are going to behave in exactly the same fashion. So you can suppress the z-axis and make it two-dimensional. Hope that is clear. Hope that is clear. Okay, good. So again, the next point that I want to tell you is that this displacement of this white fellow, so I'm going to represent that here. So here is our x-axis, this is our y-axis, this is the white fellow, and it is getting displaced in this particular direction along the xy plane. This displacement can be resolved into two components. One is the x component, that is u1, and another one is the y component, that is v1. So I have just resolved the displacement the displacement of this white fellow, okay, the nodal point 1, one along the x direction, that is u1, and another one along the y direction, that is v1. Hope that is clear. Okay, so coming back, and I can represent that here. The displacement along the x direction, it is u1. The displacement along the y direction, it is v1. Pulling the same trick for nodal point number 2, the displacement along the x direction is u2, and the displacement along the y direction is v2. The displacement along the x direction of the nodal point 3 is u3, and the displacement along the y direction of the nodal point 3 is v3. Hope that is clear. Okay. So now you know what is u1, v1, which is the displacements that are reckoned one along the x direction and the y direction. Same u2, v2, same u3, v3. And also the displacements or functions of x and y, they are definitely not functions of the z-axis. Okay, this is a physical scenario. Once the physical scenario is clearly established, then mathematics is going to take over. Okay, now in the next page, I'm going to do the first step in deriving the shape functions. So step number 1 is to assume a trial function. Assume a trial function. I'm going to assume a simple trial function for the displacement along the x direction. That is that is the displacement along the x direction. It is a function of x and y. Definitely it is not a function of z direction. I think we have had the discussion. And the trial solution that I'm going to assume is a0 plus a1x plus a2y. Well, I am not going to assume a3z. You know the reason why, because the displacement is not a function of z-axis. And I'm not going to assume a3x square y squared or a3xy. The reason is because it is a constant string triangular element. We are going to assume a very simple trial function, so that if you differentiate this trial solution to find the values of strains, the strains within the triangle is going to be constant. I will give explanation about that, and at the end of this video, or in a separate video, I can give an explanation of what exactly is a constant strain triangular element. Okay, so this is the first step. In exactly the same way, I can assume the displacement along the y direction, which is a function of x comma y. It can be the same way, a0 plus a1x plus a2y. Okay, I'm sorry. Maybe you want to assume this way. There is a3 plus a4x plus a5y. Okay. Now, I'm going to call this as equation number A, and I'm going to call this as equation number B. And I'm going to take this equation number A, and I'm going to rewrite equation number A in matrix form. And I'm going to concentrate only on equation number A, not on equation number B, because whatever changes that I do to equation number A, the same changes would apply for equation number B. Okay, so equation number A, u of x comma y, I'm going to write that in matrix form. It is 1xy a0 a1 a2. So I have written equation number A in matrix form. I will call this as star equation. Okay, I'm going to call this a star equation. So step number 1 is to assume a trial solution and write the trial solution in matrix form. 1xy, a0, a1, a2. So if you do this matrix multiplication, you end up with this equation back. Okay, hope that is clear. Now this is step number 2. So here is step number 2, is to apply the boundary conditions. Step number 2, I'm going to apply the boundary conditions. So what are the boundary conditions? Going back to the initial triangle that we have assumed, you can see that the nodal point 1, the coordinate values are x1 comma y1. The nodal point 2, the coordinate values are x2 comma y2. The nodal point 3, the coordinate values are x3 comma y3. Now at x1 comma y1, what is the value of displacement along the x direction? u1. That's right. Okay, that's what I'm going to do. That is applying the boundary conditions. At x1 comma y1, The nodal point displacement along the x direction is u1, along the y direction is v1. That's the boundary condition. At nodal point 2, the displacement, that is at x2, y2, the displacement of the nodal point 2 along the x direction is u2, along the y direction is v2. Similarly, for nodal point 3, the displacement along the x direction is u3, along the y direction it is v3. So the displacement of the nodal point 1 along the x direction is u1, and the displacement of the nodal point 2 along the, that is at x2, y2, the displacement along the x direction is u2. At nodal point 3, that is at x3, y3, the displacement along the x direction is u3. If you apply these boundary conditions on this star equation, on the trial solution, on the trial solution, that is equation A, so instead of xy, you put x1, y1, u becomes u1, okay? And if you apply the second boundary condition, xy becomes x2, y2, displacement u becomes u2. If I apply the third boundary condition, that is xy becomes x3, y3, and the displacement along the x direction u becomes u3. Shall we do that? So u becomes u1 at x1, y1. So that is at a0 plus a1 x1 plus a2 y1. U becomes u2 at x2, y2. So a0 plus a1 x2 plus a2 y2. U becomes u3, that is a0 plus a1 x3 plus a2 y3. You can call this as equation number 1. You can call this as equation number 2. You can call this as equation number 3. Write the 3 equations in matrix form. That's going to be our next step. So step 3 is to write 1, 2, and 3 in the form of a matrix. Shall we do that? So I'm going to do that. So here we go. Write the 3 equations in matrix form. u1, u2, u3 is equal to 1 x1, y1, 1 x2, y2, 1 x3, y3, a0, a1, a2. I have written the 3 equations in matrix form. Now, everything is known in this equation, assuming that u1, u2, u3. So that is a grand assumption that you are making here. And assuming that you know the coordinate values, x1, y1, x2, y2, x3, y3. So the unknowns are a0, a1, a2. Maybe you can call this as M matrix, okay? I'm just giving a name here. If you want to find the values of a0, a1, a2, you have to throw this M matrix on the other side. It becomes M inverse. Okay, shall we do that? So the unknowns are a0, a1, a2, a0, a1, a2. If you want to find the values of a0, a1, a2, then you have to throw this matrix to the other side. So that becomes M inverse. So 1x1, y1, 1x2, y2, 1x3, y3, and it is inverse into u1, u2, u3. So I have thrown this matrix to the other side. Now the question is, how do you find the inverse of your matrix?